Greetings everyone, this is Mr. Mullen. In this podcast I'm going to review some ideas about simple pendulums. So if I have a pendulum, let's say that I pull back some object and there is kind of its equilibrium position where that object would normally hang, and I pull it back. Let's say the pendulum has some length L and I pull it back some angular displacement here, and as I pull it back it goes across this circular path and forms this little arc length S, and so as I pull back this object, as it starts to swing down and come back and forth like we've seen a pendulum do, I'll notice that it just keeps repeating the same motion over and over again. And so for this pendulum to count as simple harmonic motion, what we need to have is a situation where Hooke's law holds true. And I'll say what that means in a second. So for a pendulum to count as SHM, simple harmonic motion, there needs to be a restoring force, and that restoring force has to be proportional to the displacement from equilibrium. So as I pull this back here, there has to be some force that increases as there's more and more displacement. It has to be proportional. So when I look at this and I pull it back here, what is the restoring force? Well, I know that the force of gravity is going to be pulling vertically straight downward. And if I take a look at what's actually acting in the direction of this kind of arc length displacement, and that would only be the x component of that gravitational force. Now as I pull it back farther and farther and farther, what happens is as I pull it back at a higher angle, that gravitational force component responsible to restore the pendulum back is going to increase as well. So we can actually work with this as this is our force that's going to be restoring, FGX is our restoring force. Now I know that the force of gravity is just m times g, so that little x component would be mg sine of theta. And what we're going to do is we're going to do a approximation here, and this only works. Pendulums are it's only going to be simple harmonic motion when the angle is really small. So what I'm going to do is I'm going to make the approximation that gravitational restoring force is going to be equal to m times g times theta. And the reason why I'm going to make this approximation is because theta is almost nearly equal to the sine of theta when the angle is really small. Now if you don't believe me, type in a really small angle, sine of that angle, you're going to get a number very close to 1. And so multiplying anything by a number close to 1 is essentially saying that it's the same number. So I'm going to put this approximate equal sign rather than equal sign. So we're going to make an approximation. That means pendulums will only act in this way, behave like a simple harmonic oscillator when there's a small angle. And knowing what I know about the angle in relation to that displacement, that arc length, I know that theta is equal to S over R. So I'm going to replace S with the arc length, and my little r, my little radius is actually going to be the length of that pendulum arm. So there we go. So when I look at this all together now, FGX is approximately equal to I'm going to factor out the s, and I'm going to leave m times g over L times the arc length. What I'll notice when I rearrange it in this way is that m times g and L, those are all constants for my pendulum. Okay, these are all constants, and s is that changing arc length, and Fg is that force. So when I look at Hooke's law, and I look back at this expression I've written, where k, that constant for Hooke's law applying to a spring, is equal to some thing that's not changing about the spring, and there's some restoring force, and there's some displacement. What I'll notice is that this works out, that the displacement, in this case the arc length, is directly proportional to that restoring force. So yes, pendulums do exhibit SHM. Are simple harmonic motion oscillators. Okay, we have that direct proportionality there. So when I look at, we've already looked at the period of a spring oscillator is 2 pi times m over k. That's for a spring. So if I look at the situation I've just kind of presented here, we've got 2 pi, and I'm going to go ahead and plug in the mass. Now this is a period for something that's oscillating in SHM. K is going to map to m times g over L. So I'm going to actually substitute that in here, m times g over L. And when I do that, and we got masses canceling, my new expression is 2 pi times the square root of L over G. And so what this is going to be the period of a simple pendulum. So this was our SHM oscillator that we already are familiar with, the spring. And so this P, this is going to be the period of a simple pendulum. So now we have a new expression. Notice, mass does not affect the period. There's no m in there. It canceled out. It was independent of the mass. And you'll notice that the amplitude is not in there either. So that's not going to affect anything about this, the period of this. So I'm just going to do a little quick example. This is example number 7 in your handout. It says calculate the length L of a long pendulum. I'm going to assume it's a simple pendulum that completes 12 full oscillations every minute. So they're giving me an amount of cycles per unit of time. They're giving me how frequently this thing is oscillating. It's 12 cycles for every 1 minute. And so what I can do is I can convert that into cycles per second divided by 60. We're going to find that we've got 0.2 cycles per second. And so that is our frequency. But I want to know the length of a period, and I need an equation that has L in it, and I'm going to be looking at that equation for the period of a oscillator. So I look at my equation sheet, I got Tp is equal to 2 times pi times the square root of L over G, but they give me the frequency. So I remember that frequency and period are reciprocals of each other, and I can use that frequency to get the 5-second period. And if I know that the period is 5 seconds, then I can use this new equation to find that unknown length of the spring. And when we solve for L, we're going to get that this must be a 6.2 meter long pendulum. The other way I could do this is if I wanted to, I know that the frequency is equal to the reciprocal of this little guy. So, if you wanted to do it that way, you're going to get the same answer. So we could plug it all into that one as well, and that will work if I don't even want to find the period, and I just want to go with that route. All right, that's been a little quick lesson on simple pendulums, and I hope this has been helpful.